Hello everybody. Today I want to explain about a star cluster. Let me share my screen. Yeah. Here you see the diagram of Higgs-Boson diagram for different globular cluster. They are from the pre-main sequence to globular clusters. You see, we have different range of stars in different range of magnitude, luminosity. And you see from here and here, you see, for example, here the stars which are in O, B, and A type stars, they leave the main sequence sooner and fast. And you see here or here. But if we have, for example, G or K type stars, they leave the main sequence after a million years. And you see that it is continuous, not like this. And they leave the main sequence very slowly. And we can see the continuous path of them for red giant branch and subgiant branch. So it shows that these are old clusters, and this is a young cluster. For example, also this is young cluster because O and B and A type stars of that leave the main sequence very fast, and they are young stars, and this is young cluster. Here you see 47 tests, and it shows that the distance of that, or NGC 104, the distance of that is 4,500 parsec, and the diameter is 31 arcminute, and the metallicity is minus 0.76 dex, and the year is 12 gigayears. And so it shows with these parameters, it shows that this is a globular old cluster. And you see also it is red. And the type of the stars of that is mostly G, K, and M type of stars. And you see that they leave the turn-off point is here, and they leave the main sequence in a continuous path. Here you see in the main sequence stars, if we have red giant, in red giant it has a helium core, it has hydrogen and helium shell. In main sequence star, like our sun, it has a core, but hydrogen and helium are in its shell. They are in surrounding of the core. And in asymptotic giant, you see that we have carbon, oxygen core, and we have helium shell, and also we have helium and hydrogen shell, the other shell. And in horizontal branch star, we have a core, and then we have helium surrounding of the core, and then we have hydrogen and helium also surrounding of the this area. And we can see in open clusters, we can observe main sequence stars and red giants and white dwarfs also. But we cannot observe asymptotic giant and horizontal branch star because they are old. You see, they are old because they have carbon oxygen burning in the core, and they leave the main sequence later, and they are old, and we can see them in old clusters or globular clusters, we call them. But for young clusters, we can see red giant and main sequence star and white dwarf. In open, and the question is how we can distinguish that if we see a red giant in open cluster or globular cluster, it is a young star or it is an older star. Because maybe you think that we just see red giants in the globular clusters, which they are old. But we have red giants in open cluster as they are young stars. And how we can distinguish them? We can say in open clusters and old classes we have red giant, but if it is massive, it is in the open cluster. If it is not massive, the red giant is not massive, it is in the old cluster. And if we see the iron in metallicity, it is an old star. And if it has helium line, it is a young star. Here you see Hyades with the age of 8.90. The distance is 45 parsec, and the metallicity is plus 0.17 dex. And you see that it's a young cluster, open cluster, and we see the difference range in luminosity from young stars until older stars. You see some red giant here. And I told you that if they are massive, they are old. If they are not massive, if they are massive, it is a young star. If it is not massive, it is an old star, each of them. Here, it's a typical example before Gaia for the year 2006. And you see that the first estimates of the fundamental parameters of the relatively bright galactic open cluster NGC 5288. In 1 pixel, it is some characteristic for observation of the NGC 5288 from this open cluster. And we have 15,688 stars in the complete field of the NGC 5288. You see, and different main sequences due to fore and background population. You see that if you want to fit the isochrone, it is somehow hard because there is the main sequence, and maybe we have different isochrone from that. We can measure that. And this is the first image of the first proper motion measurements from PRESEP, and the distance is 190 parsec. And these are the foreground stars or background stars. And these are the star cluster, the stars of this star cluster. And you see the proper motion of them that they measure it. And the typical example after Gaia, a new method for unwilling open clusters in Gaia. New nearby open clusters confirmed by data release 2 or DR2. Here you see two open clusters For example, here you see the center of the cluster and the other stars from the center to other directions. And this is for proper motion. And this is the main sequence of this cluster. And this is another cluster. Maybe you think that in this picture, the center is here, but it's not. Because if we want to measure the number of the stars in this star cluster, you cannot measure from here because it is not symmetric. So where is the symmetric center is here. So we can say that the center of this cluster is here. And then we can count the stars from here as a symmetric. And here is its proper motion, and this is the main sequence and this cluster. But you see some gaps that we call them Hertzsprung-Russell gaps. Because of these large gaps in many new star clusters, maybe we call them not star clusters, maybe they are numeric star clusters, not physical star clusters. And in here, you see 3 different star clusters from Hipparchus and Tycho, and which they are before Gaia. And in here you see the proper motion for distant star clusters is almost 0, because if we measure there's a star cluster and they are so far from us, we can say that we cannot measure the proper motion of them, and we just see them that they are constant. So the proper motion of them is near 0. But the other stars, which they are moving, so they are not from that cluster. Only field stars with large proper motions can be sorted out. These are almost only foreground stars, as you see here, which they are not related to these star clusters. And in here you see NGC 186819, one of the best cases, more than 3 measurements for each star, and 6,571 radial velocities for 1,207 stars with 3.5 meter telescope. And here you see the main sequence of this cluster. And in here we can say that in star clusters, as I told you, they are not all of them are not related to the cluster. Some of them are foreground stars, which you see here, and just in this region we see the number or members of the star cluster. And it is the other way of showing that for non-members and members. And we can say in here that stars in star clusters have the same proper motion and the same radial velocity. And you see that the other stars have not the same proper motion and radial velocities. So just in this region, members of this region have the same proper motion and the same radial velocity. So just these stars are related to the one star clusters, and the others are foreground stars. So integrated properties, we have integrated spectra and we have an integrated photometry, integrated color. In integrated spectroscopy, we put the spectra in the center of the cluster and measure the spectra. And in integrated photometry, we measure the sum of the all magnitude in the center of the cluster by putting a slit in the center of that cluster. And for Pleiades, as you see here, as it has 2 degrees in the sky, and it is a very large and bright cluster, open cluster, and how we can measure the integrated spectroscopy of that. We can say if we want to do integrated spectroscopy of the Pleiades, we know the absolute magnitude and the color. So then we can sum up them, the absolute magnitude and color, and then we can measure the integrated spectroscopy. And here you see the star clusters in the Andromeda galaxy, which is near to us. And in here, we see that we can see that with integrated spectra, we can measure the let me tell you later, or in here we see there's a problem about the integrated spectra. And what's the problem of that is we see a lot of foreground stars. And how we can distinguish which is the real and which stars are the member of the cluster. So for solving this problem, we can say that we put the slit in 2 or 3 positions, then we subtract them and find the stars of the star cluster, not the foreground stars. And we have this problem just in the Milky Way. Also it is Andromeda, but we can measure it. We can have an example of that. If we can say it as a Milky Way. Why Milky Way? Because it is near to us and we are in the Milky Way. But for other galaxies, no, we don't have this problem. Like Andromeda, we don't have this problem, as you see here. And in here you see the integrated spectra, which is related to age and metallicity. With integrated spectra, we can measure the age and metallicity of the star cluster, but we cannot measure distance and reddening. For example, in here, you see these are young stars because they have a lot of emission lines. Young stars have H alpha and H beta emission. But for older stars, we don't have emission. We mostly have absorption, as you see here. And in young stars, we have more fluctuation, as you see here, a very long and huge line here. But in old stars, we mostly have continuous line, as you see here. And also about metallicity, as you see the metallicity of here and here, if we measure and compare them, we see that the metallicity of here is stronger and they are different from the metallicity of here, which they are weak. So these are old stars and these are young stars. In integrated color, We can sum up all stars and get the integrated color and integrated magnitude. If we can measure the integrated color, we can measure the total mass. And we can say from the photometry, we can measure the total mass. For the total mass, we can use isochrone. As you see here, they are for massive stars, which they have 40,000 ms, and these are 25 mass of the sun. And you see the isochrone of them. And they are red giants that they shifted to their left, to the red color in the left. And you see that this is a Hertzsprung-Russell diagram for these stars. And F in here is the fraction of red giants or supergiants in the open clusters. Thank you for your attention and see you next time. Bye.